Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arif.me. The other way is to download the notebook file from course GitHub account arif. And all the notebooks of this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 7.4 of the 7th module, overview of natural language processing, for the course titled Tools and Techniques for Data Science. Well, the title of today's session is Feature Engineering. My dear students, this is our fourth session, and I keep repeating that NLP encompasses all the tools and techniques that enable computers to understand and respond to human languages in written, verbal, and signed form. In the previous two sessions, we completed the second phase of NLP pipeline, and that is text pre-processing. We covered text cleaning and basic text pre-processing in lecture number 7.2, and in our previous video lecture, that is 7.3, we covered some advanced pre-processing tasks like stemming, lemmatization, part of speech tagging, and its applications like named entity recognition and co-reference resolution. Today we are going to talk about the third phase of our NLP pipeline, and that is feature engineering. At an abstract level, the process of converting textual data into vectors of real numbers is known as text vectorization. And the goal is that those numbers should be able to tell the meanings of those words. Well, there exist various approaches of converting text into vectors, which can be broadly classified into two categories. The first category use frequency or statistical based approach, and these label encoding, one hot encoding, bag of words or n-grams, and this TF-IDF as well falls into this first category. The second category says don't count but predict. This category is also known as word embeddings, which maps a single word into a vector of real numbers of maybe 3 to 400 dimensions. You can design and build your own models using deep learning techniques, and you can use some existing pre-trained models as well, like Word2Vec by Google and Fast Text by Facebook. I think I have opened a rapid burst of different terms, but don't worry, by the end of today's session, you will have a very fair idea of what all these techniques are after doing a hands-on implementation of all these in Python, inshallah. So let's move on to the agenda of today's session. My dear students, I will do scuba diving of these five concepts. Uh, these five frequency or statistical based approaches of text vectorization. So make your oxygen tanks ready. These context predicting models, commonly called embeddings, they use neural network based on deep learning based models as well for text vectorization. And since we have not yet covered the deep learning module of this course, so in this part I will just swim around on the surface and will use the Word2Vec model of spaCy library, and maybe I will touch upon the Gensim library as well for Word2Vec. Well, my dear students, I strongly recommend that for a crystal clear understanding, you should make time and watch this video from start to end. But if you have already the basics in your pocket, then you can jump onto the subtopic of your interest by clicking the specific time link in the description box below. Okay, so Well, my dear students, let us start with a quick overview of the concept of feature engineering and text vectorization. Uh, if you do not have a machine learning background, let me first tell you what do we mean by features in machine learning, because they are a bit easy to understand. Suppose we want to predict the price of a house, and of course, the price of a house depends on the city uh, in which it is located, its size, covered area, number of bedrooms, and so on. These are called features, which are shown over here. In this table, I have shown 7 features. It appears the name of cities is a nominal data type which can easily be converted into numbers by assigning a unique number to every city. Moreover, I think the feature trees nearby has no role in predicting the price of the house, so we can remove this column. So every instance of a house can be represented by a vector of 6 dimensions, or a vector having 6 numeric values. And these numeric values can be fed to some machine learning algorithm to train and later predict the price of the house. Okay. My dear students, now consider this comment. Arif YouTube lectures are amazing. And suppose I want to classify this comment as either positive or negative. Naturally, I will use some classification machine learning algorithm like maybe naive Bayes for this purpose. But the problem is that machine learning algorithms are not capable of processing such plain text. They require numerical numbers as input to perform any sort of task such as classification or regression or maybe even clustering. And the same problem exists for image as well as voice data. My dear students, in textual data, a feature can be a single word, a phrase, maybe a sentence, a paragraph, or maybe a complete document. Okay, I think now we have a fair idea as to what do we mean by the term feature in NLP. Let us see how we can convert a feature into a vector of number. Okay, let me describe the concept of feature engineering and text vectorization with an example. Consider a text phrase Dr. Khurram Shehzad, another text phrase Dr. Muhammad Arif Bhatt, and a word Pakistan. Now, question is how can we represent these words as vectors of numbers? Well, my dear friends, I have created 5 features whose values I think will be able to tell the meanings of these 3 words. The first feature is this a person? And since Khurram is a person and Arif as well, so they have a value of 1 for this feature. And since Pakistan is a country, so it is having a value of 0 for this feature. The next feature is it healthy or fit? So Khurram and Arif has a value of zero point 0.8 and zero point 0.9 for this feature respectively. And since Pakistan is facing economic and political crises other than the deadly floods which have come in Pakistan, so I have assigned a value of zero point 0.6 to this feature. May Allah bless my country. Ameen. Well, the third feature is location, and naturally, Khurram and Arif has a value of 0 for this, while Pakistan has a value of 1 for this feature. The fourth feature is does it has 2 eyes, and the fifth feature is does it has a government. So, my dear students, these are some of the features that I have just thought of. You can think of more features to describe these words. Thus, feature engineering is nothing but finding out different attributes that can represent a word, a phrase, a sentence, a paragraph, or even a document. And assigning numeric values to these features and representing them as a vector is called text vectorization. Remember, over here I am classifying a person and a country, so I have designed these features. If I have to classify a cat and a dog, the features will of course be different. So this vector, this blue vector is representing this text Dr. Khurram Shahzad. This red vector is representing the text Dr. Muhammad Arif Bhatt, and this green vector is representing the text Pakistan. So what is feature engineering or text vectorization? So after the what part, the next question is, why do we need to represent a word or phrase as a vector of number? My dear students, one possible answer is we cannot feed text to machine learning algorithm, and another answer can be uh, we can perform a lot of operations on these vectors. We can add them, subtract them, and find out similar vectors from them. Like in this example, you can easily see that the two vectors representing Dr. Khurram and Dr. Arif are more similar as compared to the vector representing Pakistan. Let me move ahead and try to describe this with the help of this image. So why to do text vectorization? My dear students, consider this document 1 containing this sample text that says I am playing football while he is playing basketball. Period. Football is played in a ground. Period. You have to do a goal in football. Let's say that I want to vectorize this document 1 using the count or number of occurrences of just these two textual features, football and basketball. In this document 1, the word football appeared 3 times while the word basketball appeared once only. So this document can be represented as a 2D vector 3, 1. And this top left image shows the graphical representation of this two-dimensional vector that represent this document 1. I hope this makes sense. On the x-axis I have kept football, and on the y-axis I have kept basketball. Okay, now consider this document 2 whose text I have not shown completely, but assume that it has the word football appearing 6 times and the word basketball appearing 2 times. So the 2D vector representation of this document 2 is 6, 2. And this top middle image shows it graphically. Similarly, this document 3 has the word football appearing 2 times and the word basketball appearing 7 times. And the 2D vector representation of document 3 is the 2, 7. And this top right image shows the graphical representation of this vector, shown in green. Well, this image or graph at the bottom left shows all the 3 vectors representing the 3 documents in a single 2D Cartesian plane. Now let's suppose that we want to figure out the similarity between these 3 documents, which are shown in blue, in red, and in green. My dear students, the angle between the 2 vectors actually represent the similarity between the vectors, or maybe the documents. Note that the angle between the 2 vectors representing document 1 in blue and document 2, this red one, that is 3, 1 and 6, 2, is 0. So we say that document 1 and document 2 are exactly similar. On the contrary, the vector representation of document 1, that is this 3, 1, is making an angle of let's suppose 35 degrees with the vector representing document 3, that is 2, 7, shown in green. So they are not completely similar. My dear students, to make it more intuitive, we map the degrees from 0 to 90 degree to a value between 0 and 1 by taking the cosine of the angle between the two vectors. And this is called cosine similarity. And let me describe you with the help of this table. If the angle between two vectors is 0, the cosine of 0 is 1. Therefore, the two vectors or documents are exactly similar. And similarly, if the angle between two vectors is 90 degree, the cosine of 90 is 0. Therefore, the two vectors or documents are completely different. And similarly, I hope these values are also making sense. My dear students, in our linear algebra for data science video, we talked a lot about vectors, and we also discussed Euclid distance or L2 norm, as well as the Manhattan distance or L1 norm. Let me take this opportunity to tell you about the cosine distance as well, which can be obtained by subtracting the cosine similarity from 1. And this is also shown in this table. Do note that uh, when the cosine similarity between two documents is 1, the corresponding cosine distance is 0. And when the cosine similarity is 0, the cosine distance is 1. I hope these two columns are making sense. Well, now a $100 question, and that is shown in red over here. We can easily represent and visualize a vector having two dimensions or two features only as shown in this image. But in real life, our textual data has hundreds and even thousands of features, and their corresponding vectors have also the same number of dimensions. And the question is, how can we compute the angle and in turn the cosine similarity between two such vectors having, let's suppose, 100 dimensions? Uh, and this is what I have discussed in detail in my linear algebra videos, and here is the formula to do that. So the cosine similarity between two vectors u and v having any number of dimensions can be computed by dividing the dot product of the two vectors with the product of magnitude of those two vectors. Ah, uh, my dear friends, I'm sorry if I have gone into unnecessary details, but I think it was important to make you realize as why do we need to vectorize our text before discussing different techniques to vectorize. Let's move ahead. So after answering the what and why question, let me answer the third question, and that is how to do text vectorization. This diagram summarizes the process of transforming a text corpus into different input formats for a machine learning model. In summary, we can vectorize using frequency or statistical based approaches like label encoding, one hot encoding, bag of words, and n-grams and TF-IDF. We can also use prediction based approaches like word2vec from Google and fast text from Facebook. Each of these techniques have their own pros and cons and should be chosen according to the dataset and the problem at hand. So let us start understanding and implementing them one by one. And the first is label encoding. My dear students, the first two techniques of text vectorization are very primitive and are not used in NLP. This label encoding and one hot encoding. This is because of their limitations. However, to set the stage right for better understanding of the remaining techniques, let me spend a few minutes on them. And let us start with the label encoding. Let me reiterate few terms first before I start telling you what do we mean by text vectorization. And the first is document. My dear students, a document is a single text data point that can be a tweet, a comment on a YouTube video, or maybe a review of a particular product by a user. A corpus is a collection of all the documents present in a dataset. And finally, for the time being, you can think of a feature as every unique word in the corpus. Now let me describe label encoding with an example. Consider a corpus that consists of three documents as shown. Arif help his students, Arif assist his students, Arif lectures are great. Well, for label encoding, we first build a vocabulary of this corpus, which is a collection of all the unique words in this corpus, and then we assign a unique number to each word. And this is shown as a dictionary over here. And to transform our document as a vector, you simply do a lookup. So this is the vector representation of these three documents. So Arif help his students is represented as a numeric vector 5431. I hope this is making sense. Okay, so these are the limitations of label encoding technique. First of all, the size of the vector is not fixed. You can see we can have more number of words in a document, so the size of the vector is as per the number of words in that document. Unfortunately, every machine learning algorithm accepts some fixed size input. So this is a big limitation. The second limitation is that there can be a new document having a word which is not there in our vocabulary. So we will not be able to encode it. This is called out of vocabulary problem. And finally, if you see in document 1 and 2, the word help and assist are almost similar in meaning, but these two words have completely different representations in label encoding. So label encoding cannot capture the meanings or semantics of a word. Let me move at. So due to these limitations, this label encoding is not used in NLP applications. Now let us talk about one-hot encoding, which we normally use to encode categorical variable like gender by assigning a value of 0 for male and 1 for female. I think we have seen this in our pandas session. Well, consider the same sample corpus having three documents and the vocabulary, that is a set of 8 words. We encode every word using a binary vector of fixed size, which is the length or size of the vocabulary, which is shown over here. Since our vocabulary size is 8, so we represent every word by a binary vector of size 8. Note the vector representation of the word Arif shown in this row having a value of 1 under the column Arif, and rest everywhere we have zeros. Excuse me. Similarly, the vector representation of this last word, lectures, has a value of 1 under the lectures column, and rest all are zeros. Well, the vectorized representation of these three documents, doc1, doc2, and doc3, using one-hot encoding is shown over here. And you see this is actually a sparse matrix. I hope this is making sense to you all. And let us discuss the limitations of one-hot encoding. The first three limitations are same. Although the vector size of each word is same in this case, however, documents having different count of words will have different size. Well, a new limitation of one-hot encoding is that this technique is memory hungry. For example, in this toy example where a document has 4 words and the corpus has a vocabulary of 8 words, each document is represented by a sparse matrix of size 4 by 8. 4 rows, 1 for each word of document, and 8 columns, 1 for each word of vocabulary. So due to these limitations, we neither use label encoding nor one-hot encoding for text vectorization in NLP. Okay, My dear students, a bag of words encoding is the most used text vectorization technique and is mostly used in text classification tasks. Before we make our hands dirty to practically do it in Python, let us have a quick conceptual understanding of bag of words encoding technique. Consider this a sample corpus that consists of three documents. Arif YouTube lectures are amazing. I like YouTube lectures and Khurram also like YouTube lectures. Arif YouTube lectures are great. So these three documents consist of 5, 10, and 15 words respectively. The vocabulary consists of 10 words, which is represented as a dictionary over here. Well, instead of encoding every word separately as done in one hot encoding, we encode each document as a fixed size vector of the size of the vocabulary, which is 10 in this case. If you observe, each document is converted into a frequency vector having a count of words. For example, see the vector representation of this document 2. It has the word Khurram coming once. So we have one over here. You see the word Khurram is coming once. The words lectures, like, and YouTube, the lectures, like, and YouTube are coming twice in this sentence, doc 2. So that's why we have the value 2 under the lectures column, the value 2 under the like, and the value 2 under the YouTube column for this doc 2. My dear students, instead of count, the values can be just 0 and 1 as well, representing the absence of presence of a word respectively. But over here I have mentioned the frequency of the words. Well, this representation of these three documents is also known as document term matrix that describes the frequency of terms that occur in a collection of documents. Each row corresponds to a document in the corpus. Each column represents a unique word in the vocabulary. Uh, Theoretically, the column names are the terms or words, but in reality, the column names are the indices of the words in the dictionary of vocabulary. You can map these with this vocabulary dictionary. Finally, the values inside each cell are integer values representing the frequency or count of that particular word in that document. And if a vocabulary word do not appear in a document, you place a 0 in that cell. Of course, before representing a document in a bag of words format, we perform a pre-processing to remove all the stop words which will reduce the size of the vocabulary. I have not done it over here to keep things simple for better understanding. Let us now discuss the advantages and disadvantages of this technique. Well, the main advantage of bag of words over label encoding and one hot encoding is that it encodes every document as a fixed size vector, irrespective of the number of words in the document. So these vectors can now be fed to a machine learning algorithm for training and prediction. You can see they are fixed size vectors irrespective of the number of words in a document. Let us now talk about limitations of bag of words techniques. The vector representation of a document is small in size as compared to one hot encoding. But still, if we have a large corpus having a vocabulary of, let's say, 50,000 words, then every document will be represented as a vector of size 50,000, in which most of the values will be 0. So to conserve memory, in our computers, we normally save this document term matrix using sparse representation. Soon I will show this to you. Well, the out of vocabulary still exists. Semantic meanings are not completely captured. The ordering or sequence of words in a document is not captured, and we know that in English language, the order of words does play the role to convey the proper meaning of a sentence. Finally, the vector representation of two sentences Arif YouTube lectures are great and Arif YouTube lectures are not great, they will be very similar in this encoding scheme. But in reality, we know that these two sentences convey completely different meanings. And this can be handled using n-grams, which we will see later. I think I have made you understand what bag of word encoding is. So let's move ahead and do it practically in Python. My dear students, I think we can now create a document term matrix whose columns represent the words in the vocabulary and each row represent a document in the corpus. And this can be done in three steps. First of all, we need to tokenize all the input documents. Then from the tokens of all those documents, we create a set of unique words which will be the vocabulary of the corpus. And finally, we need to populate the cells of the document term matrix with integer values representing the frequency of words of the vocabulary uh, in a particular document. Well, instead of creating manually and writing this program manually, let us use the famous scikit-learn count vectorizer class uh, that that not only creates a document term matrix of all the input documents, but also allows you to control your n-gram size, perform custom pre-processing, custom tokenization, eliminate stop words, as well as limit the vocabulary size. So let's jump into the code. Well, this code cell creates a corpus of three documents. Let me create it. And before proceeding any further, we need to import the count vectorizer class from sklearn feature extraction.text module uh, over here. We create a count vectorizer object with the default attributes. I am not passing any arguments, and we are saving it in a variable named CV. Let's check the type. So it is count vectorizer. On this count vectorizer object, one can call the fit method and transform method separately. But let me call the fit underscore transform method by passing it uh, the corpus or the raw documents. This will learn the vocabulary dictionary and will return a document term matrix which I am receiving in a variable named BOW, bag of words. Let me execute it. Okay, so let us check out the attributes and methods of the count vectorizer object using the dir function. Let's execute. So there are quite a bunch of these displayed over here. The vocabulary underscore attribute of count vectorizer object contains the vocabulary, which we have seen above as well. You see the corpus vocabulary is displayed as a dictionary. So we have the curly braces over here having 10 tokens or unique words indexed from 0 to 9. Moreover, note that the indices are assigned in alphabetical order. So this also is assigned a number of 0. This amazing is assigned a number of 1. This and is 2, and so on to finally this YouTube is assigned a number of 9. Uh, we can also use the get underscore feature underscore names method of the count vectorizer object that will display the words only in the vocabulary, of course sorted in alphabetical order. So this is giving me a warning. This is going to be obsolete. Let me use the latest method for the purpose. Great. Do note that the single character word I is not there in the vocabulary. Uh, we can check out the shape of the document term matrix that is returned by the fit transform method of the count vectorizer object. So we kept it in the variable box, so it is 3 comma 10. So it is a 3 by term matrix, a 3 by 10 matrix, which means there are 3 rows as there are 3 documents in the corpus, and there are 10 columns, which is actually the vocabulary size. Okay, so let me now just print the. Okay, so this also says that this is a 3 by 10 matrix saved in sparse matrix representation. Instead of 30 values, it has just stored 16 elements. My dear students, you can also use the toArray or the toDense method of this count vectorizer object to display the document term matrix, or simply the matrix that shows the count for every vector. So this is our document term matrix that exactly match with what we have seen while conceptually understanding the bag of words encoding. So this is the uh, vector representation of document 1. This is the vector representation of document 2. You see the last 3 words are 222. Let me show you over here as well. So document 2, lectures like YouTube 222. I hope this is making sense. Let us understand the sparsity of the matrix as well. This code counts the total number of cells in the matrix, which is 30. The n and z attribute of the bag of word object returns the count of non-zero cells, which is 16. So over here I am just calculating the percentage. So the percentage of non-zero values in the document term matrix is roughly 53%. Well, my dear students, since this is a toy dataset, that is why around 47% of the cell contains zero values. In real examples, you will see that around 97-98% of the cells of a document term matrix contain zero values. So in order to save memory and at the same time speed up algebraic operations on these vectors, we use a sparse representation of matrices. Okay, so let us now save the corpus as a document term matrix in bag of word encoding, and this code shall do this job by first importing the pandas library and then using the data frame method. Note the first argument is the sparse matrix converted to dense matrix, and this second argument over here is the column names, which I have got using the get underscore features underscore names underscore out method this time of the count vectorizer object. Let me execute it, and this has been displayed. So this is your count document term matrix, and of course if you do not want the column names, you can do it like this as well. So good job done, good job done. Okay, my dear students, in order to improve or fine-tune the results on your datasets, you can tweak different hyperparameters of the count vectorizer method. I strongly recommend that you should go through all the hyperparameters available at the link shown over here, and let me touch upon some important ones. First of all, vocabulary is none. This is the default value. You can pass a Python dictionary of your own. Lowercase, the default value is true. That means it converts all the documents to lowercase before tokenizing. Tokenizer is equal to none. The default tokenization in count vectorizer remove all special characters, punctuation, and single characters. If this is not the behavior you desire, you can pass your own custom tokenizer. You can do that. Stop words is equal to none. That means this count vectorizer method will not remove the stop words. Preprocessor is equal to none. You can pass a function over here as well that do the pre-processing of your choice if you want to do stemming and lemmatization. Binary is equal to false. By default, as we have seen, this shows the frequency count. If you are not interested in the frequency of the words, rather you just want to know whether the word exists in the document or not, you set binary is equal to true. Max feature is equal to none. If you want to put a limit on the number of features, that is the vocabulary size, you can mention it over here. And finally, this n-gram range is used for creating n-grams. Soon we will see this with an example ahead. Okay, here we are. My dear students, we have seen that in a simple bag of words, the vocabulary consists of single unique words of the corpus. The limitation is the sequence or ordering of words is ignored in that case. And we know that in languages like English, the order of words does play the role to convey the meaning of a sentence. Uh, a bag of n-gram model is quite similar to bag of word model. It represents the text as an unordered collection of its n-grams instead of mm, single word tokens. For example, Arif YouTube lectures are good and Arif YouTube lectures are not good. In case of 1 gram, it will be really difficult to comprehend the meaning of these two sentences. However, in case of bigram, the two bigrams are good in first sentence, not good in second sentence, will make the difference. Okay, consider the same corpus consisting of these three documents. And here is the vocabulary of bigrams and the document term matrix. I hope this is making sense. And similarly, this is the vocabulary of trigrams and the document term matrix. Over here as well, the columns are sorted in alphabetic order. My dear friends, we have talked about the n-grams concept in our previous session of pre-processing, I think. If you do not have a fair idea about the unigrams, bigrams, and trigrams, please watch that portion of that video. Do note that in bigram, document term matrix under the YouTube lecture columns over here shows that in document 1 and 3 we have a single occurrence of this bigram, while in document 2 we have two occurrences of this bigram. These are the advantages and disadvantages of using n-grams. Let me simply move ahead and do this in Python now. My dear students, once again, we can use the count vectorizer method of sklearn and use its n-gram underscore range argument whose default value is a tuple with two values 1, comma 1. A value of 2, 2 and 3, 3 will create a vocabulary and later a bag of bigrams and trigrams respectively. A value of 1, 3 will create a vocabulary of unigram, bigram as well as trigram. Let's understand this with help of an example. The code in this cell will make this happen. Note the n-gram range argument which is passed 2, 2 over here to the count vectorizer method. Let me straight away execute it. You see, my dear students, let us compare now this document term matrix with the image that we discussed above. So this is the document term matrix for the bigram, and this is the document term matrix for the bigram that we discussed. So these are exactly same. And of course we can save it as data frame. Okay, so this example, I'm sorry for this typo, uh, will create the document term matrix using the trigram. Note the n-gram range argument is 3, 3 this time. Let me execute it. Of course, you can compare this as well with the document term matrix that we discussed above. They will be exactly same. So far, so good. So let me move ahead. Well, my dear students, we have seen that in back of words encoding, the values of our document vector represent the number of times a particular word appear in that document. So we can say that it treats every word of a document equally, irrespective of its actual importance. This way, it gives more importance to some unimportant words that appear more frequently in a document. For example, words like since, as, can, any, and, the, of, it, they can have high frequency, but these words are not important. This will take the attention of machine learning model away from less frequent but more important words. So let us use another text vectorization technique, and that is known as TF-IDF. That stands TF stands for term frequency, and IDF stands for inverse document frequency. Well, this term frequency tells us how important a term is in a particular document by assigning more weight to a term that is appearing more frequently in a document. Well, document frequency tells us how important a term is in the entire corpus. And the intuition behind taking its inverse is that more common a word is across all documents, the lesser its importance is for the current document. Let us do a step-by-step computation of these for better understanding. And let us start with term frequency. Well, my dear students, in literature, I have found these three formula for computing the frequency of a term T in a specific document D. The TF-IDF vectorizer method of scikit-learn uses this first formula. So I have used this first formula to compute the term frequency of, uh, of these three documents of a corpus. And it says that just count the number of times the term T occurs in a document D. And this table shows the term frequency of each term in each of these three documents. Note that document 2 has a total of 9 words, excluding this single character word I. Uh, and over here you can see that uh, the word lectures 1, 2 is coming 2 times, so we have 2 over here. The word like 1, 2 is coming 2 times, so we have a 2 over here. The word YouTube is coming 2 times, so we have a 2 over here. Well, the size of the corpus vocabulary is 10, so each document is represented by a vector of size 10. And of course, this we have seen before as well. Great. So let's move ahead and talk about inverse document frequency. As said before, document frequency tells us how important a term is in the entire corpus. But since we want to penalize frequently occurring words across all the documents, so we take the inverse of the document frequency. This way, the IDF of rare words in the corpus will be large, while the IDF of very common words in the corpus will be close to zero. Once again, in literature, there are different formula to compute the IDF, and the most common is shown over here. So So inverse document frequency of a term T uh, in the collection of documents D is equal to the total number of documents in the corpus represented by N divided by the document frequency, that is the number of documents in which the term T appears. A question may come to your mind, and that is why we are taking the natural log of this. Well, my dear friends, in a corpus having large number of documents, if a word is appearing in only one document, then the IDF value of that term will be very large. So we take the log to dampen its effect. My dear friends, the TF-IDF vectorizer method of scikit-learn makes some modification to this formula. And the formula that TF-IDF vectorizer method with the default argument of smooth IDF is equal to true is shown over here. You can see a constant 1 is added to the numerator as well as in the denominator to prevent any non-zero division, rather to prevent any zero division. And the reason of adding a 1 to the IDF value is that the terms that occur in all the documents will not be entirely ignored. Soon I will show you this once I will be calculating the values of different terms. And let us compute the IDF value of the term, let's say Arif in all the documents. IDF of Arif in the entire corpus, which is equal to 1 plus log of 1 plus 3 of 1 plus 2. This 3 is the value of n, which is the total number of documents. And this 2 is the document frequency, the number of documents in which the term Arif is appearing. So since Arif is appearing in 1 and 2 documents, so therefore we have a value of 2 over here. I hope this is making sense. Anyway, so the final IDF value for Arif for the entire corpus is 1.28768. My dear students, this vector over here shows the inverse document frequencies of all the vocabulary of the corpus. Note that the terms lectures and YouTube that are appearing in all the 3 documents are given an IDF value of 1, not 0. And this is because of this modification. This way, these 2 terms will not be entirely ignored in the overall calculation of TF-IDF. So this is what IDF is. So we are done understanding and calculating the term frequencies of terms in all the 3 documents separately, and inverse document frequencies of the vocabulary of the corpus as well. The final TF-IDF score can be calculated by multiplying the term frequencies vectors of each document with the inverse document frequency vector of the entire corpus. So after multiplication, this is the document term matrix containing the TF-IDF score of each term in each cell. My dear friends, I hope this is making sense. However, one final step we still need to perform, that is to normalize these TF-IDF values. And this is done to avoid large documents in a corpus to dominate small documents. And for this, you divide each TF-IDF value of a document with the respective Euclidean norm. So you compute the Euclidean norm of document 1, document 2 and document 3. The Euclid norm of document 1 has a value of 2.8, document 2 has a Euclid norm of 5.29 and document 3 has a Euclid norm of 2.86. So this is the final document term matrix showing the vectorization of the 3 documents with the TF-IDF values. Well, do note that the higher the TF-IDF score of a term in a document, the more relevant that term is in that document. For example, in Doc 1, uh, the term amazing is the most relevant term, having the highest TF-IDF value of 0.5918. Great job done. Well, my dear students, I think now you can programmatically compute this document term matrix without the use of any API. But for the time being, let me move ahead and tell you how simple it is to calculate these vectors using scikit-learn TF-IDF vector class. So here is the code for that. Well, consider this corpus of three documents as seen above. Let me execute it. The code of this cell over here is importing TF-IDF vectorizer class from sklearn and then creating a TF-IDF vectorizer with default attributes. Done. Now we are just calling the fit underscore transform method on the TF-IDF vectorizer object. This will learn the vocabulary dictionary and will return a document term matrix having TF-IDF values, which I am receiving in the variable name TF-IDF over here. And let's print the vocabulary. So this is the vocabulary. You can see this is the same vocabulary which we have done above as well, and the feature names. And let's check out the shape of the document term matrix over here. It should be of course 3 by 10. And of course this will be a sparse matrix, and we can convert it to a dense array using the toArray or the toDense method. Great. And finally this is the data frame of uh, the document term matrix containing TF-IDF scores as we computed above manually. You see this YouTube in document 1 and document 3, it has a value of 0.34, and in document 1, 0.37. Let me show this over here. 0.34, 0.34 and 0.37. So these are the calculations which exactly match with what TF-IDF vectorizer has done for us. My dear students, TF-IDF technique of vectorization is used in information retrieval. However, it still has almost the same limitation as we have discussed in case of bag of words encoding. So these techniques do not give good results for problems like machine translation and question answering systems, where a deeper understanding of the context is required to achieve great results. So let's move on to the next family of techniques called word embeddings. Great. My dear friends, word embeddings are techniques that map a single word as well as an entire document to a dense vector of fixed size ranging from 50 to 300 dimensions, and that captures the semantic meanings of the word as well. Word embedding techniques can be prediction based, and its examples are Word2Vec introduced by Google in 2013, this fast text introduced by Facebook in 2015. Another category of word embedding techniques are frequency based, and its example is global vectors or GLOVE, that is introduced by Stanford. And this GLOVE technique actually iterates through the corpus and create a co-occurrence matrix. Well, interested students should go through these related research articles, and let me give you a bird's eye view of this word-to-vec technique and a bit of its usage using a spaCy and Gensim library. Okay, so my dear students, let me adjust the size of the screen so that you can view it properly. Since we have not covered our deep learning module and Word2Vec use a neural network to generate vectors. So we will not do a scuba diving in this domain. However, let me make you swim on the surface. Well, word-to-vec model use two approaches. The first is a continuous bag of words where we have several input words which are the context words. The projection tries to predict the highest probability word against the context of these surrounding words given as input. Well, in simple words, the input are context words which are used to predict the target or the output word. The second word-to-vec approach is skipgram, described in this right image. In skipgram, the input is a word. The projection tries to predict and output the weighted probabilities of other words that are going to show up around the context of this input word. Simply saying, the input word is used to predict the context words. So let me repeat. In SIBO or continuous bag of word, the input are context words which are used to predict the target or output word. In skipgram, the input word is used to predict the context words. Okay, let me try to describe this with an example. Well, consider these four words: king, queen, woman, and princess. The vector representation of these words using a bag of word or TF-IDF encoding will be completely different. And these techniques are not concerned with the meaning of these words. And this we have seen in the previous part of our today's session. On the contrary, when these four words are passed to some trained word-to-vec model, it will automatically extract roughly 300 features related to each word as well as compute the corresponding values. And to do this task, the model is already trained on a very large corpus of text, maybe the entire Wikipedia pages. For example, on such pre-trained model, one such pre-trained model that spaCy use is the large model for its English language. And another which we are going to today is the Google News model that is trained on the Google News dataset. But for the time being, uh, this image shows a hypothetical vector representation of these four words with a set of features like royalty, masculinity, femininity, age, and so on. Do observe the values of these features in all the four vectors. The royalty value for king, queen, and princess is high. Similarly, the masculinity value for king is high while is low for the rest. I hope this is making sense. Okay, my dear students, let us use spaCy large model for English language for doing word-to-vec. Uh, we have already downloaded and used spaCy small model, but it doesn't contain word vectors. So we have to download this large model. Note this LG. So this is going to take a bit of time. I have already done that. So just let me import spaCy and load this large English model. So this is just a warning. You can ignore it. Anyway, uh, once it is done, let's check out the total trained word vectors in the vocab, taking the length. So this model has word vectors for a vocabulary of over 5 lakh words. Let's check out the shape. So this means each word is represented as a 300 dimensional vectors containing 300 real values. Okay, so Let's check out the vector representation of different words using this pre-trained model. So let me check out for, let's suppose, line first. So this is the word line, and we have a vector of 300 values. Great. Let me check out for man. Let me check out for, let's suppose, king, as well as for queen. And finally, let me check out for the word Arif. So this means the word Arif do not exist in the vocabulary of this model. Therefore, this is out of vocabulary problem. Good. Great. Fine. Let me pass three words to the model: line, cat, and Arif, and use this dir function on a specific word. Let's say this line. Let me execute it. So these are the attributes that are associated with each word or token. Let us use some of these attributes for better understanding. And let me straight away execute the code of this cell and describe you this. Well, my dear friends, this dot text contains the text, which is line, cat, and Arif. This dot has underscore vector returns true if there is a vector related to this word in the model, otherwise return false. Note that since Arif is not there in the vocabulary of this model, therefore we have a false over here. Is underscore OOV returns true if the word is not there in the model's vocabulary. You see, Arif is not there in the model's vocabulary, so it has returned true. Finally, this vector underscore norm attribute returns the Euclidean or L2 norm of this vector, which is shown over here. Please do play around with the rest of the attributes for better understanding, and let me move ahead. Well, let's talk about the cosine similarity. The code of this cell use actually this uh, similarity method, which is used to compute the similarity between two words. Let me execute and then I can describe. So this time we have these three words: python, cat, and pet. And they are mapped to a vector. Each is mapped to a vector of 300 dimension. We can use the cosine similarity to measure how similar these vectors are to each other. So I have done a nested loop and have compared them. So you see this python, python. Their similarity is 1. The similarity of the cat with the cat is 1. The similarity of pet with pet is again 1. If you see over here, let's suppose this cat and pet. These two words have uh, a similarity of 0.73, as you can keep cat as a pet. However, if you check out over here, python and pet, they have a similarity of 0.18, as we normally do not keep python, which is a snake, as a pet. Let's see this one more example having two words, love and hate. Note that the two words love and hate, although being opposite in meaning, have a similarity of 0.57. The reason of this is most of the time they are used in the similar context. I just wanted to tell you this. And finally, this code cell, uh, I have used the cosine underscore similarity and cosine underscore distances method of scikit-learn library. So you can see the cosine similarity between the two words representation. Love and hate is 0.57, while the cosine distance is obtained by subtracting this value from 1. And this is what we have discussed in the beginning of today's session as well. My dear students, I think that is an okay kickstart on word vectors using spaCy. Let me spend a few minutes on using the Gensim library as well. Okay. Uh, my dear students, now we will be using this pre-trained Google News model for word vectorization. You can download the file from this link, and do keep a note of the path where you have saved it. Well, it contains word vectors for a vocabulary of 3 million words and phrases that they have trained on roughly 100 billion words from Google News dataset. So you just need to install Gensim if you have not done so before. Then we need to import the two classes word2vec and keyed vectors from gensim.models package. Let me load this model, this file which we have downloaded just by clicking this link. This is the path. This will take a bit of time because this is a large model. So it is still working. You can see the static over here. So this keyed vectors class is used for this purpose. This load underscore word to vec underscore format method is passed this path where this file is located. So this is done. Now we have the model in this variable named w2v. Let us now check out the vector representation of different words. Let me check first of all the vector representation of line and its shape. Great. Let me check out for man. So once again, this is a 300 dimensional vector. Let me show you king. Good. Okay, so let me touch upon some very common methods. The first is most similar. My dear students, this model has a method named most similar to which you pass a word and it returns the list of 10 closest or most similar words along with their similarity score sorted in decreasing order of similarity. Let me run it for your understanding. So I'm asking it to list the top 10 similar words which are similar to king. So naturally, the kings is the most similar. Then we have queen, we have crown princes, we have prince, and so on. Let's check out for man, for snake, and for Facebook. You see, we have reptile, lizard, python, cobra, and so on. And for Facebook, we have Facebook, then Twitter, Facebook, then Facebook.com, and so on. Great. I hope this is making sense. Well, if you have two words and you want to check out the similarity between them, you can use the similarity method. Check out. So it's pass two words, it convert these two words to their corresponding vector representations and then compute their cosine similarity. You see, man and woman are very much related, while man and python are not. Okay, this doesn't match is also a very commonly used method of this model, which is passed uh, a list of words. As usual, it first converts these given words into vectors and then computes their cosine similarity. It returns the word that is the least matching with others. So man, woman, cat, boy. Can anyone tell me which is the least related word? Well, yes, that is cat. Great. Okay, so one last thing, my dear students, uh, that I want to show you is that we can perform mm, vector arithmetic with these word vectors, which will return a brand new vector. Uh, so king, man, and woman are the three words whose vector representation, of course, exists in this model. We are subtracting man from king and adding woman to it. Of course, the resulting vector is not directly associated with a single word exactly of this model. Uh, so actually, these three lines you see, these three lines are actually creating the vectors of these three words. This line is performing the arithmetic, that is king minus man plus woman. Oops. And this most similar method will return the list of top 10 matching words. Let's just execute. And you see the output. Queen is there at the second position. So after you subtract a man from king and you add woman to it, you get a queen. Okay. Well, can any one of you guess what will we get after we uh, subtract uh, England from its currency symbol dollar and then add Pakistan to it? Let's check this out. Great. So we have got Pakistani currency symbol rupees. Well, my dear friends, do think of more such puzzles and uh, you can share your code in the comment box below. Great. So that is all for today's session of feature engineering phase in NLP pipeline. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.